Hey everyone, welcome to the first lecture in our series on interactive online learning. I'm Sanjaman Chaudhary, an assistant professor at Cornell and research scientist at Aurora. In this series, we will try to understand the fundamental fabric that ties all of robot learning. How can a robot learn from online interactions? Our quest is to build a one true mathematical framework that we will wield to conquer various problems in reinforcement learning, imitation learning, model predictive control, and motion planning. So let the journey begin. Let's begin by asking a fundamental question. How do we humans learn new skills? So think back to the time you learned a new skill, say juggling. One hypothesis may be that you observe an expert juggler juggle the ball, and you observe for lots and lots of times, and then you simply acquire the skill. But we all know from our experiences this is simply not the case. The reality is that humans learn by interacting with the world. So they probably begin with a set of strategies, and they try out the strategy and get feedback from the real world. As a consequence, they have to adapt the strategy and discover new failure modes and keep repeating this process. So, humans learn by interacting with the world. Now, let's contrast this with how we mostly train robots today. For instance, how we train robots to do self driving. There are essentially three simple steps. First, go collect data up front, typically from expert human driving. So data here is a pair of state and actions. Step 2, train a model that maps state to actions. This mapping is commonly referred to as a policy pi. So you define a loss function for this policy and go minimize the loss function. And finally, step 3, you validate your model and deploy if your model's good. So your training error matches your held out validation error. Now, unfortunately, when you do this, you see that your policy totally fails. And this is because your train and test distributions were mismatched. So let's dig into why this happens. Now, there can be various reasons why a train and test mismatch happens when you're dealing with real world robots. And all of these various reasons have one thing in common, which is that the robot never gets to see all the data all the time. So imagine this hypothetical scenario of binary classification where the picture shows all of the true label distribution. So pluses here are positive class and minuses are negative class. And if the robot saw all of this data, it could easily come up with this boundary to separate the two. However, the robot at any given point of time is only seeing a small window of data. So if it sees the first cluster of data, it would conclude that the classifier should be a horizontal line. On the other hand, if it sees this second cluster of data, it would conclude that the classifier would be a 45-degree sloped line, right? So you get different classifiers just because you saw different sections of the data. And one reason this can happen is because data changes over time, as for example, as the seasons change. A second, more interesting reason is when you're collecting data on policy. So in this case, the output of the learner affects the states that the robot visits, which feed back in as input. So feedback drives covariate shift between train and test. And finally, the most extreme version is when the robot is engaged in a multi-agent game, where the robot is playing against an adversary that can control the data distribution that the robot sees. And it is this third setting that we'll consider because if you can solve this one, you automatically can deal with any other kind of distribution shift. And so this is the setting we'll refer to as interactive online learning, where we will think of the learner being engaged in a game with an adversary. In each round of the game, the learner plays a policy pi, and the adversary returns a loss function. Now, this simple framework is actually pretty powerful, and recurs through various fields in robot learning. For example, in imitation learning, uh, the loss function could be how well the policy imitates a human expert. In reinforcement learning, the loss function is the value of such a policy. In model predictive control, it is a cumulative cost of such a policy. And in planning, it could be the length of the shortest path. But the question that we will focus on is what makes for a good interactive online learner? What is the goal of the learner in this setting? So let's introduce a little bit of math to formalize interactive learning. First, our goal is to learn a policy pi. Think of a policy as a mapping from inputs x to outputs y. Let capital Pi be the set of all such policies. Finally, we need a loss function, L, that maps a policy to a real number. Now we're going to play a game. This is going to be a game between a learner and an adversary. So the role of the learner is to play a policy pi. The role of the adversary is to select a loss function L. So we are going to iterate over rounds of the game. There's going to be a total of t rounds. And in every round, the learner picks a policy pi from the set of all policies, and the adversary picks a loss function LT. Okay, now we will define a notion of regret of the learner for choosing a sequence of policies. Think of regret as the difference of two terms. The first term is the sum over per time step losses. So it's LT pi t. This is the total loss of the learner. And the second term is the loss of the best policy in hindsight. So what is the best policy in your policy class that minimizes the total loss? Let's try to build up some intuition for this game by looking at it very visually. So it's best imagined as a table where every row of the table corresponds to the various policies you can select, and columns corresponds to the rounds of the game, so the losses you receive. Now let's say at round 1, you went with policy 2. Then you observe a loss for all policies in that round, and you see, wow, you got a high loss of 1.0. So you switch to policy pi 1 in round 2, and you see that gets a high loss. But since policy 3 looks good, you switch to that in round 3, and that's not as bad. And so every round you're picking different rows, and you're observing the loss you get. Okay, so given such a table, how do we compute the regret of our learner? So recall that the regret is the difference of the per time step loss of the learner minus the loss of the best policy in hindsight. So to compute the first term, simply add up the losses of all the numbers in the red cells, because that's what the learner picked. And to compute the second term, look at all the rows and pick the row that has the minimum cumulative sum. It's as simple as that. The difference of these two tell you the regret of your learner. If your learner was really good, it would have picked pi 3 all along, and as a result have a regret of 0. But of course, the learner is not omniscient, and therefore may end up having quite a high amount of regret. Okay, so what is our overall goal? Our overall goal is to be no regret, which means be as good as the best policy in hindsight as time increases. So drive the average regret to 0 as time tends to infinity. So if you have a really crappy learner, you're not going to be no regret. In fact, if you plot the average regret over time, it's going to plateau to this non-zero value. But if you come up with a clever strategy, it'll actually go to 0. And that essentially means your total regret value is sublinear in time. So it could be as good as square root of t or square root of t log t and so on. You would also like your total regret to scale to large policy classes, so it better be log card pi, right? And so typically, we'll be talking about various algorithms that have different relationships with t and pi. But the overall goal is to do as well as the best policy in hindsight, so to achieve a zero average regret as time tends to infinity. Now let's go back to the realm of robot learning, and we'll see how this game that we just talked about occurs in various domains like imitation learning, reinforcement learning, and planning. Let's begin with imitation learning. We'll particularly be talking about a paper by Ross, Gordon, and Bagnell that reduces imitation learning to interactive online learning. So, what is imitation learning? In this setting, you have a learner that's interactively querying a human for what action they would do in a particular state. So, the learner is trying to learn a policy that maps states to actions. The loss of a policy is, did the policy select the same action as the human in that state, right? And so on states visited by the policy pi, query the human for their action and penalize for not selecting that action. So let's take a concrete example of trying to teach a robot to drive around a racetrack like an expert human driver. We're going to be studying an algorithm called Dagger, which is a no regret algorithm. Specifically, an example of follow the regularized leader that we'll talk about in upcoming lectures. So, the way Dagger proceeds is at every round of the game, we begin by executing the learner to visit a set of states. Now, initially, of course, the learner is pretty crappy, so it goes off the track. We then query the human for their actions. So what would the human do in these various states? Once you have these human actions, that effectively defines your loss function for that policy. Now, Dagger advocates for aggregating data and training a new policy on the aggregated data. So at every round of the game, you're going to play a policy that minimizes loss on all the losses it has seen thus far. And this is a key bit that helps Dagger be no regret. So you keep playing the game, keep collecting data, keep updating your policy, and since Dagger is no regret, eventually you'll do as well as the best policy in your policy class. Okay, let's move on to reinforcement learning. Now, reinforcement learning has various ties to regret analysis, but we are going to talk about work by Osband, Van Roy, and Russo that looks at reinforcement learning through a Bayesian lens. So, what is reinforcement learning? You have a learner that's interacting with an unknown MDP to find the optimal policy. So the learner here, once again, just like before, maps states to actions, but the loss of the learner here is the cumulative rewards of executing the policy pi, right? So you roll out pi in your unknown MDP, count the rewards, and add them up. Okay, let's take a look at an example of a cartoon MDP to make the point. So you have a robot trying to get to a pot of gold, and there are multiple paths to get there. Most of these paths involve crossing a rope bridge, and the robot doesn't know how reliable these rope bridges are. On the other hand, there's a paved path that the robot's pretty sure is reliable. So the robot has to interact with the world to collapse uncertainty. We'll now talk about an algorithm called PSRL, which is an example of a Bayesian online learning algorithm. So at every round of the game, the robot samples a potential MDP from a prior over MDPs, given what it's seen, right? So, maybe it samples an MDP that says, hey, all the bridges are feasible to traverse. It then goes ahead and plans with an MDP. So probably plans to take the second shortest bridge, then executes the plan and observes state, action, next state transitions. So upon executing this plan, it falls off the bridge and realizes, whoops, I can't traverse it. It then updates its priors and repeats the process. So maybe this time it tries the first bridge and falls off that and realizes, okay, the only feasible path is probably the paved road, and confirms that when it attempts it. And just like Dagger, this algorithm may sound very simple, but it's actually one of the most powerful algorithms to do exploration exploitation in reinforcement learning. Finally, last but not least, let's talk about real-time planning. So this is some of my own work with Brian Hu on posterior sampling with anytime motion planning. Now, a key bottleneck in robot motion planning is collision checking. So checking the geometry of the robot against environment to see if it's feasible. That's a very expensive step. And so the idea is, can we have a planner that's interactively evaluating paths to find increasingly shorter feasible paths over time. So the policy pi here is actually a path, which is a sequence of edges on a graph. And the loss function in this case is the length of the shortest feasible path that the algorithm has found till now. So suppose we have a robot that's trying to plan from start position to a goal position, and it doesn't explicitly know the location of all the obstacles. It can only discover them online while collision checking paths. Once again, we're going to look at this problem through the lens of Bayesian online learning. So we're playing T rounds of the game. In each round of the game, the robot maintains a prior over the validity of edges. So which edges are infeasible because they're in collision, and which edges are feasible. And the robot samples a graph from this prior. So maybe it samples, hey, every edges are feasible. And then using this graph, it invokes a motion planner that returns the shortest path, which, by the way, is pretty cheap to compute because the robot's not doing any collision checking. It already knows the status of every edge. So this is a super fast process. Then the robot goes and evaluates this path in the real world. So it has to call a collision checker. Now, this is the expensive bit. When it does that, it realizes, whoa, some of these edges are actually in collision. Now, based on this observation, it goes and updates the posterior over edges, right? So it marks the edges it saw to be feasible, but even nearby edges are marked as potentially infeasible. Based on this, it computes a new path that maybe goes around the obstacle. And when it checks this path, maybe it's feasible and it has a feasible path to the goal, but that's not necessarily the shortest. So it has to keep repeating this process of guessing what the shortest path might be, checking edges, updating its belief until it's able to thread the needle and find the shortest path from start to goal. So this is a really cool example of how online learning can really help speed up real-time robot motion planning. And with that, let's pop back up and talk about what this lecture series focuses on. So clearly, interactive online learning is fundamental to robot learning, but what is a unified framework that allows us to reason over all the algorithms that we saw? This lecture will focus more on insights behind these algorithms rather than fixating on the bounds. And of course, it'll be biased towards algorithms that have shown promise in real robot applications. If you're interested in understanding the fundamentals of online interactive learning, there are a whole host of wonderful resources. Here are some of them. The first one I would recommend is Shai Shalev-Shwartz, small survey on online learning and convex optimization. Lattimore and Szepesv have a wonderful new book called Bandit algorithms. It's fairly exhaustive. Slivkins has also a wonderful book called Introduction to Multi-Armed Bandits that I would recommend. And of course, Bubeck has books, blogs, and tutorials that are very, very informative. So I would highly recommend checking all of these out. Now, as a fun exercise, we're going to try to distill an entire series of lectures into a few core concepts that recur over and over again. The first concept is that when the learner has full information, the problem reduces to that of hedging. In other words, how should the learner optimally hedge against an adversary shifting loss functions? So if the learner doesn't change its options at all, then the adversary wins. If the learner changes options too eagerly, the adversary wins. What is the sweet spot in the middle? The second core concept is that in the partial feedback setting, the learner doesn't actually get to see the loss for all the various policies, right? So in this setting, how can the learner optimally trade off between exploration, just figuring out the loss of unknown policies, and exploitation, picking the most promising policies? Now, the cool thing is all the algorithms we look at will eventually look like that of online linear optimization. So we will begin by looking at finite policies, which we will lift to a probability space, and that'll look like online linear optimization. Conversely, we will also look at online convex optimization, which we will push to subgradient space, and that'll look like online linear optimization. So there is a massive reduction even within the field of online interactive learning that kind of unifies all concepts. And this brings us to the end of the first lecture. So the key challenge we discussed today is how can a robot learn in interactive online setting? This was motivated by a fundamental problem in robotics that the data distribution changes. It can change over time. It can change as the robot visits new states, or it can change if the robot is in a game with other players, and we particularly fixated on the game setting. What is the goal? The goal is to achieve no regret. So recall that regret is the difference between the total learner loss minus the total loss of the best policy in your policy class. And no regret essentially means do as well as you could if you could see all the data up front. Finally, we saw how interactive learning is at the backbone of various robot learning paradigms like imitation learning, reinforcement learning, planning, model predictive control. We leave you with an open question, which is there truly a one ring of interactive learning? Is there one algorithm to bring them all and in darkness bind them? The answer is yes. It's called mirror descent, and we will dedicate an entire lecture to talking about mirror descent in the near future. Till next time.